Water level measurement in nuclear reactors. In a previous lecture, we have learnt about boiling water reactors (BWR). In this lecture, water level measurement in BWR is discussed. Nuclear reactors are boilers. In case of nuclear reactors, heat source in a nuclear reactor is the fuel rods inside the reactor. In case of regular boilers, heat source in a regular boiler is a fossil fuel that is charged from the outside. What makes a boiler in a nuclear reactor more difficult to operate is that turning off this internal heat source is harder because stopping the nuclear reaction is more difficult and time consuming than it is to close a fossil fuel feed valve. It is essential to keep the fuel rods covered with cooling water so that they will be protected from overheating and melting. The accurate knowledge of the level of cooling water both inside and outside the core is essential. Request: it is hoped that this session is going to be useful to you. Please press like. Please subscribe. Light water reactors, that is LWR. Reactor types using light water as a neutron energy moderator and heat transfer medium together with slightly enriched uranium fuel have become the dominant technology. There are two types of light water reactors: pressurized water and boiling water reactors. Here we are explaining the difference between PWR and BWR, that is pressurized water reactors. PWRs prohibit boiling in the core and use secondary heat exchangers or steam generators to produce steam, which powers the turbine generator. Boiling water reactors. BWRs produce steam directly in the reactor core and pass the steam to the turbine generator. This is moisture separator. This is the jet pump, and this here is the suction of the jet pump. During operating conditions, water level in boiler water reactors should be below moisture separators so that supply of saturated steam to turbine is dry. Water level should be kept above the suction of the jet dispenser so that cooling water is always available to reactor core. This is the reactor core, and this line indicates the shroud around the reactor core. Figure in next slide shows a boiling water reactor BWR and the traditional method by which the cooling water level is measured in many existing BWRs. In a BWR, the core is surrounded by a shroud. BWR, Boiling Water Reactor, cooling water level measurement. This is the jacket-like space between the shroud and the outer wall of the reactor. The cooling water enters into this jacket-like space between the shroud and the reactor wall and is pumped downward by the jet dispenser. The jet dispenser is not shown in this diagram. This space is in core and this space is out core or X core. Water travels down X core on the outside of the core and then rises up in core inside the core. As it rises, the fuel rods heat it and it starts to boil. As the water travels upward, steam bubbles are formed, as a result of which the steam to water ratio rises and hence the water swells. This space is X core. In many BWRs, the in-core water levels and the steam water ratios S by W are not measured. Instead, they are measured only X core between the shroud and the reactor wall. Under emergency conditions, when the cooling water pump stops and if the X core water level drops below the suction of the jet dispenser, which otherwise would pump the water down into the core, this X core measurement no longer reflects the in-core water level. Consequently, X core level measurement can become useless during loss of cooling emergencies, such as when the electric power to the cooling water pumps is lost. This is LTN, level transmitter narrow range. This is LTW, level transmitter wide range. In most nuclear power plants, the X core level is measured by two differential pressure type level transmitters. One has a narrow range LTN and other a wide one LTW. The narrow span transmitter LTN is naturally more sensitive and is a better indicator of the X-core boiling water level, that is of the location of its surface, while the wide range transmitter LTW detects the total X-core hydrostatic head in the reactor. This is the condensate pot and this is the condensate drain line, which is joining condensate pot with the steam space. Almost without exception, these transmitters are of the differential pressure type and are both installed with condensate pots which provide their water filled reference legs, that is wet legs, that are connected to their high pressure sides. In order to cool and thereby condense the steam on this high pressure side, the condensate pots are usually uninsulated and the excess products of condensations drain back into the reactor through the connection of the side of the pot. So the condensate level in the pot remains constant. The level transmitters shown in figure are both inverse acting. If the level rises, the transmitter output signal drops because the hydrostatic heads on their high pressure sides are constant and correspond to the weight of a water column generated by the condensate pot. This water is at ambient temperature because both the pot and the connecting piping are uninsulated. Therefore, a maximum X-core level inside the reactor results in a zero signal from the transmitters, while a zero level causes a maximum output signal. The reliability of this measurement depends on the assumption that the wet leg is full of condensate and that it is at ambient temperature. During an accident, these assumptions can be wrong because the condensate from the reference leg can either drain or can overheat. This is the low pressure tap of the LTN. In addition, once the X-core level in the reactor drops below the low pressure tap of LTN, this differential pressure transmitter will be looking at a zero pressure difference. That is, both taps will be connected to steam and its output signal becomes useless. Even under normal operating conditions, because the water in the reactor is boiling, both differential pressure cells detect the hydrostatic head, that is mass of water, and not the level. This condition also varies with load, because when the steam pressure drops, the steaming rate increases. Swelling occurs, and when the steaming rate is reduced, the steam pressure rises, the shrinking occurs. The more bubbles form, that is swelling, the higher is the actual level, but lower is the density of the ex-cold water column, and therefore the detectors will under-report the level. Inversely, as the steaming rate drops, shrinking phase, the density increases, the actual level drops, while the level reported by the transmitter increases. In other words, when the surface of the boiling water rises, swelling, the level reading drops, and when the boiling rate is reduced and therefore the water level drops, the level reading rises. Some operators and designers do not realize that the differential pressure cell outputs can correctly indicate the level of the boiling surface of the cooling water only if the measurement is corrected for density changes. Therefore, these level measurements are either unreliable or useless. Since the operators know that these level measurements are unreliable, they often disregard them, disconnect the automatic level controllers, and try to manipulate the level manually. This is dangerous and unacceptable. Request: it is hoped that this session is going to be useful to you. Please press like. Please subscribe.